What's up, everybody? It's Mr. Prevet back again with another FRQ review for you guys. Today, it is the 2021 FRQ number 3. We got some volume, we got some area, we got a little bit of everything going on in this question today. I'm excited about it. This is a tough looking question, especially for a non-calculator section. Like just first glance, you see some scary functions, which that can always kind of be a turnoff looking at some of these questions when they're just hard, like on observation. But we're going to go through it together and it will be great. As always, thank you guys so much for watching. It means the world to me that y'all would watch these videos. I hope that I'm being helpful and that I'm encouraging you to work on calculus, get better, grow your skills, and develop. But let's dive into this. Question number 3. It says a company designs spinning toys using the family of functions y equals cx times the square root of 4 minus x squared, where c is a positive constant. The figure above shows the region in the first quadrant bounded by the x-axis and the graph of this function for some c, right? Each spinning toy is in the shape of the solid generated when such a region is revolved around the x-axis. Both x and y are measured in inches. Okay, so, I can draw the graph that they have set up right now. But they have this function that looks like this, right? And when it is revolved, it creates that top shape, right? So it's revolved figure looks something like this. No, a top, it spins on the tip of it, right? But let's look at these questions together. Let's dive into it. So part A. Part A says find the area of the region in the first quadrant bounded by the x-axis and the graph of y equals cx root 4 minus x squared, for c is equal to 6. So really what they're saying is they want us to find the area, the region bounded by 6x root 4 minus x squared. Okay. So I know that area under a curve is equal to the integral over our bounds of just the function. So it'll be 6x root 4 minus x squared dx. Now my first bound is clearly just x equals 0, right? We're at the origin. Now this second bound is a little bit more difficult. But it's where my y value equals 0. So 6x root 4 minus x squared has to equal 0. X can't equal 0, so I can just forget about that. So 4 minus x squared equals 0. So 4 minus x squared equals 0. X squared equals 4. So x equals plus or minus 2. X obviously has to be positive in this case. So our second bound is x is equal to 2. So now we have this whole integral that is just the area of this function. Now, for this integral, I've got an inner and an outer function. So we're going to have to do a u substitution to solve this integral. My u substitution should always just be the inner function, right? So I'll do u equals 4 minus x squared. And my du would become negative 2x dx. Okay, so now this integral, right? This will become the square root of u, right? Which is great. But I want negative 2x dx. I have 6x dx. So what do I need to multiply the inside and the outside by? Well, on the inside, I need to multiply by negative 1/3, right? I'll multiply by negative 1/3 on the inside. And then on the outside, right, I'll multiply by negative 3, which is just the reciprocal of negative 1/3, and that will balance it out, right? So this new integral for the area, we'll deal with the bounds at the end, but it becomes the square root of u, or I'll write it as u to the 1/2. And then negative 2x dx is du. And then we will have this negative 3 on the outside. Now my bounds are important, right? My bounds previously were in terms of x, right? But now we need to convert them to being in terms of u. And to do that, we're going to plug them into our u substitution. When I plug in 0, I get 4 minus 0, which is equal to 4. When I plug in 2, I get 4 minus 2 squared, which is equal to 0. Now we clearly see that my bounds are in the wrong order. I could just evaluate this regardless. I like having them in the right order. And when they're in the right order, and I flip them, I will negate the value of this integral. So this equals the integral of 3 times the integral of 0 to 4 of u to the 1/2 du. Okay, so we're almost done, right? I just need to use power rule. So this will become u to the 3/2, or 3u to the 3/2, divided by 3/2, evaluated from 0 to 4. Dividing by 3/2 is the same thing as multiplying by 2/3. So those 3's will cancel out. And I will get 2u to the 3/2 evaluated from 0 to 4. When I plug in 4, I get 2 times 4 to the 3/2, which is like the square root of 4 cubed, which is equal to 8, minus 2 times 0 to the 3/2. 0 to any power is just 0. 2 times 0 is obviously 0. 2 times 8 is 16. And that is our final answer to part A, right? We also want to be careful for this one. If we were to think about the units, right? They said that x and y were both measured in inches. We're measuring an area, so this would be inches squared, right? If we really wanted units. It doesn't specifically ask for it, but it's always better to include units if you can. Okay. So that is part A. A little bit difficult, right? Definitely a challenging one. Got to do a tricky integral, solving for the bounds. Like, there's a lot of stuff going on. A tricky one. We'll move on to part B. So there are only 3 parts to this question, which means we can anticipate some really difficult parts, right? So here we go. Part B says, it is known that for our function y equals cx 4 minus x squared, that dy dx equals, oh man, we didn't think it could get worse, but it did, 4 minus 2x squared divided by root 4 minus x squared. So they could have made us take that derivative. Thankfully, they were cool about it. They just gave it to us, right? And it says, for a particular spinning toy, the radius of the largest cross-sectional circular slice is 1.2 inches. What is the value of C? Wow. So it feels like they just gave us some really random pieces of information, right? They tell us the radius of the largest cross-section is 1.2 inches. They give us these differentials and they tell us solve for C. Feels like it's coming out of left field, but let's visualize this, right? We have this spinning toy, the spinning top, with this shape, right? When it's rotated around, right, we know that the largest cross-sectional radius will be right here. So that radius is 1.2, right? That will be the biggest cross-sectional radius when we cut it. Now this is the maximum value of y, right? And at our maximum value of y, well, what's true for relative maximums? Well, we have a horizontal tangent. So our derivative is equal to 0. So let's think about what we know. Our radius is 1.2 at this point, so y has to equal 1.2 at this point. And we also know that our derivative is equal to 0. Okay, So let's try both of these things. Let's plug in y equals 1.2, and let's plug in our derivative is 0 and see what we can get based on that. So if I plug in 1.2 into this, I'll plug it in here. 1.2 equals cx times the square root of 4 minus x squared. So that's just two variables with one equation. Doesn't really help us solve much, right? But if I plug in dy dx equals 0, I get 0 equals c times 4 minus 2x squared over root 4 minus x squared. Now, the root 4 minus x squared is kind of irrelevant because for this to equal 0, our numerator would have to equal 0. Now, can c equal 0 for this top? I would say no, because earlier in the question, it tells us that c is a positive constant. So c cannot equal 0. So the only possibility is that 4 minus 2x squared equals 0. If I were to solve this, I would get 2x squared equals 4, x squared equals 2, so x equals plus or minus root 2. I know I'm in the positive side of things, so x is equal to root 2 at this point right there. This x coordinate, 1.2. Or I'm sorry, our x coordinate is root 2, our y coordinate is 1.2. So that is the point right there. But now we gotta solve for c. The great thing is we have this second equation, right? So I have 1.2 equals c times x, which is root 2, times square root of 4 minus root 2 squared. Root 2 squared is just 2, right? So this is 1.2 equals c times root 2 times the square root of 2. Square root of 2 times square root of 2 is just 2. So when I divide by 2, I get that c is equal to 0.6, which is our final answer to part B. So this one, crazy question, right? They give you a differential, they give you a y, like they give you a radius, and they say it's like the maximum cross section. All this wild information that we have to interpret correctly to get these two equations that really matter. Once we solve for x, I mean, the algebra becomes pretty simple to solve for c, but understanding this concept of at this point, my y value is 1.2, my derivative is 0, both of those are hard to get, and that's what makes this such a challenging question. So that is part B. I can kind of check here. Let's see. So that one was only worth 2 points. Part A was worth 3 points. Part B was only worth 2 points, which to me feels a little crazy. I feel like that one was really tough, but only worth 2 points. So we move on to part C, which is worth 4 points. So we can expect this one to be super tough, right? But let's check it out. It says for another spinning toy, the volume is 2 pi cubic inches. So the volume is 2 pi. What is the value of C for the spinning toy? Okay, so we have our same thing. We have our top shape. We got y equals cx times square root of 4 minus x squared. We're going to rotate this around, and the volume of this top is 2 pi. And they ask us to solve for c. Now, the volume of a revolved figure around the x-axis, if there's just one function, we can find using disk method. And the way that we do that is by saying that our volume is equal to the integral over our x bounds, which we found earlier was from 0 to 2 for all of these functions, right? And then I'm going to integrate this function squared. So this function squared is c squared x squared times 4 minus x squared, right? because I'm squaring c and x, and I'm squaring the square root, so it just goes away. Dx. But I cannot forget one very important thing about disk method. That is my pi right at the very beginning. Super easy to forget about it, but we have pi, and then we're kind of integrating our radius squared to get the volume, right? We're integrating all of these circles. So pi times the integral from 0 to 2 of this function squared. Put some parentheses because it's kind of hard to see it. But now we need to solve this integral, which I'd probably do by, expanding this first. So my volume will equal pi times the integral from 0 to 2 of 4c squared x squared minus c squared x to the 4th power dx. Now remember, c is just a constant, right? It's kind of irrelevant what c is. So when I integrate all of this, I'll just treat it like a constant, as normal. Now I know I've got the pi there. I'm going to kind of underline it and forget about it for now, just so I don't mess up my algebra, right? But let's take this integral. I know I have 4c squared x squared. 4c squared is a constant. So I'll raise my exponent by 1 and get 4c squared x cubed, and then divide it by our new exponent. Same thing for this second term. I'll get c squared, I'll raise my exponent by 1, and then divide by the new exponent, which is 5. And I need to evaluate this from 0 to 2. Okay, so now it's just some arithmetic, right? I plug in 2, I get 4c squared times 2 cubed, which is 32 c squared over 3. Minus, plug in 2 here, I get 32 c squared, but this one is over 5. So if I were to get a common denominator, get 5 times 32, which is 160, c squared, minus 3 times 32, which is 96 c squared. So I'll write out 160 c squared minus 96 c squared divided by 15. I get that 64 c squared divided by 15. Okay? Now I cannot forget that little pi. I'll tack it on there. That is our volume. But we also know our volume is equal to 2 pi, right? So now I've got this equation, 64 c squared over 15 pi equals 2 pi. And now I can just solve for c, right? I'll divide out some pi's, multiply by 15 divided by 64, and I will get c squared equals 30 divided by 64. And I could, simplify this, or I could just take square root now. And I would get that c equals the square root of 30 divided by the square root of 64, which is equal to 8. And that would be our final answer to part C, which is a really challenging question, honestly. Once again, worth the 4 points, 100%, right? Doing all of this integration, right? Which isn't too bad. It's just weird because there's the c squared values, right? But taking this integral, figuring all it out, coming up with 64 c squared over 15 pi, crazy, setting it equal to 2 pi, and then solving a challenging question, to be sure. But worthwhile, one that, when I get an answer that looks rough like this, and it's right, the feeling of joy that I feel is, unlike anything else. So I really love this question. I think it's great practice, too, to not be intimidated by scary arithmetic, right? But just pushing onwards. But that is all of question 3. Really great practice on volume and area. Also, throwing in this extra variable c really mixed things up a little bit. I was a fan, but some challenging stuff. I appreciate you guys for coming along with me on this journey of question 3, right? But I hope to see you guys on another video very soon. But until then, see y'all later.